So this would be problem F2-4, correct?
Yes.
Okay. So I understand what you're saying, and I can sort of see your reasoning, but I'll try to explain to you why the reasoning is not correct. So if we review this problem in F2-4, we are essentially given a force of 30 pounds. So we're going to have a force vector of 30 pounds acting at an angle of 30 degrees from an arbitrary axis U. Okay? So we have 30 pounds acting at 30 degrees from my axis U. And then we are also given another axis V, which is located at 15 degrees from the vertical. So we have our vertical axis here, and our axis V is located 15 degrees from that vertical. Obviously, I'm not drawing anything to scale. Okay, and now the question is to resolve that 30-pound force into components along both the U and the V axes. So I'm going to go first, see if I can try to understand your train of thought, right? So you would have thought that if we simply take 30, our 30-pound magnitude, and multiply it by the cosine of this angle, you would have gotten what's essentially a component along this line up to here. Is that correct?
Yes.
Okay. So here's where the problem is. This component that you are describing, okay, this component that you're describing really only works for this vector if your second component is a vertical component at an angle of 90 degrees. However, in this case, you don't want a vertical component. You're looking for a component along the V direction. Does that make sense?
Yeah.
Okay. So that's why you can't just take 30 cosine 30. You're going to have to actually use one of the parallelogram or laws or triangle rules. Because again, you're not adding this projection, right? You're not looking for a projection or a shadow, okay? You're actually, what you're looking is for a component that you can add up to another component along this line in order to get your 30 degrees. So what we're going to do in order to solve this problem is, instead of trying to find the rectangular components along the horizontal and vertical axes, let's consider our U and V axes to be completely arbitrary. So we have no idea about their location. And the way I would find or I would resolve this force into components is by first trying to plot my two axes. So I'm going to plot my U axis, and I'm going to plot my V axis. Okay.
So just to clarify really quickly, so the assumption that I made is that that line and then the U axis, that would be 90 degrees, but we can't necessarily make that assumption in this case, right?
You cannot. So right now, the only thing that we know is that the vertical line and the U axis have a 90 degree between them, but not V, right? So your components are going to depend on both of your axes, not just one. So, like I said, this assumption would have been right if your V-axis were completely vertical, pointing upward. So if your V-axis were at 90 degrees from your U-axis, then you can say, yes, it's sine of theta or cosine of theta. But since it's not, you cannot make that assumption.
Okay.
Okay. So yeah, so to solve this problem, typically I would like to plot my two axes at one side of the vector, and then I'm going to plot my two axes at the other side of the vector. So I have my V-axis, and I have my U-axis. It doesn't have to be perfect, but what I do want to get from this is that once you plot your axes at both the start and the end of the vector, the end result is going to be essentially a parallelogram. So what I have, if I connect this line, what I end up having is a parallelogram. And that's going to help me a little bit, because I know that this resultant force is 30 pounds. And now that I have my parallelogram, I know that this component will be my force along the U direction. And this component will be my force along the v direction. Now, Tyler, I hope you can see here, if we would have used rectangular components, my component force along the u direction should have been longer, right? But because this v-axis has an inclination, it's not at 90 degrees, then that actually makes my u component shorter than the rectangular component, okay?
Okay.
So yeah, so once we have a parallelogram, we can start working with angles, right? We know that this angle is 30 degrees. Of course, we know that this angle is 30 degrees. And we know that V has an angle of 15 degrees from the vertical. So I can plot this angle right here. I know that this is 15 degrees from the vertical. But I also know that this is also V, it's the same direction. So this is also 15 degrees from the vertical. I have 15 degrees from the vertical, and then I have my horizontal line, which is axis U, and a vertical line. So the difference between a horizontal and vertical line is 90 degrees, right? That means that this entire angle should be equal to the sum of 90 plus 15, or just 105. And that will help me find my next angle, right? Because now I know that the sum of angles in a triangle is 180. So this angle should be 180 minus my 30-degree angle minus my 105-degree angle. So how much is that? Is that 45 degrees?
Yeah.
Okay. So I have all my three angles in my triangle, and now what I can do is I can start with this parallelogram and then come up with the triangle rule. I'm going to draw my triangle. It doesn't matter if you draw your triangle up here or down here, your answer will be the same, but I can draw my triangle now, and I can apply the sine and the cosine law in order to solve this triangle. So I have my little triangle here, and I'm going to label my vectors. This is my force of 30 degrees, or 30 pounds, sorry. This is my force component along the u-axis. This is my force component along the v-axis. And I know that this angle is 30 degrees, 105 degrees, and then 45 degrees. Okay. So now that I have this triangle, I can then start applying my sine and cosine laws. So in this case, we already have all our three angles. So maybe it's easier if we just go with the sine law. So I have my sine law, and I know that my sine law says that the sine of an angle, so I'm going to say sine of 45, divided by the magnitude of the opposite side, so divided by f sub u, should be equal to the sine of 105 divided by the magnitude of the opposite side, in this case 30 pounds. If I were to take this equation, notice that I only have one unknown, and that is f sub u. So I can solve for f sub u. And what is that number?
It is 22 pounds.
Okay, so we have 22 pounds. Okay, and then likewise we can do the same thing on the other side, right? So we get the sine of 30 divided by the magnitude of f sub v equals the sine of 105 divided by 30 pounds. Once again, I apply my sine law. I have one unknown. I solve for my f sub v component, and what number is that?
15.5.
Okay. So that's how you solve this problem, and that's why you can't really assume rectangular coordinates, right? If the angle between our two axes is not 90 degrees, then you cannot use rectangular coordinates, okay? And if it makes it a little bit easier to visualize, always picture, if you have your vector, picture your 90-degree line, your vertical line as here. If your line is 90 degrees, then yes, your component is equal to 30 cosine of 30. But as you start to incline this line to the right, notice that if you rotate this line around this point, the more you incline your axis, then the more or the smaller your component will get. In this case, our line is already inclined at this many degrees, so your component is this small. So ideally, right, you should have gotten a bigger number, right? When you input a 30 sine 30, it should have been a bigger number than 22. Is that correct?
Yeah.
Okay.
It was 26.
Okay, so and that's why, right? Because the more your axis is inclined, then the smaller your magnitude will be.